This is section 4 for modeling and optimization. Example 1, find two numbers whose sum is 20 and whose product is as large as possible. So find two numbers whose sum is 20. So here's the first number, second number, and the sum is 20. And we want to maximize the product. Now the product is x times y. Now we're going to take the derivative of the product because we want to maximize this function. But I really don't want this function in two variables. I'd like to have it in one variable. So if we have to start the problem with two variables, we're going to try to eliminate one of them. Now over here, I can subtract x. So y is equal to 20 minus x. Now I'll plug 20 minus x in for y over here. Now the product is x times 20 minus x. Let's distribute. So we have 20x minus x squared. And now we'll take the derivative, and we can just use the power rule. So 20 minus 2x. Now we're going to set that derivative equal to 0 because that's where minimums and maximums can happen when the derivative is 0. So we have 20 minus 2x. We'll add 2x over, and x is equal to 10. So 10 plus 10 is 20. So the two numbers are 10 and 10. Example 2, inscribing rectangles. A rectangle is to be inscribed under one arch of the sine curve. What is the largest area the rectangle can have, and what dimensions give that area? Let's draw one arch of sine. And sine, one arch, goes from 0, and then sine is 0 again at pi. So this is 0, and this is pi. And we're going to inscribe a rectangle underneath that arch. Now we're going to assume that the rectangle is centered under the arch. So if we pick a arbitrary x value, that means this distance right here is x. Well, that means this distance over here is also x. So the base of this rectangle is pi. That'd be 0 all the way to pi, and we'll minus out these two x values. So minus 2x, there's the base. Now if we knew what the x value was, this point right here would be x, and then to find the y, we would plug that into sine, because it's the sine curve. So the y would be sine of x. So the height of this is sine of x, and then the height would depend on what the value of x would be. Now the area of a rectangle is base times height. And the base, we find out, is pi minus 2x. Pi minus 2x, and the height is sine x. So we're going to multiply by sine x. And now we want to take the derivative and set that equal to 0. Now in this case, we didn't have to use two different variables. So there's no need for a second equation to replace one of the variables like we did up here in example 1. So the derivative is first times the derivative of the second, and then plus the second times the derivative of the first, which is just negative 2x. Now we're going to set this equal to 0. And I'm not going to distribute this time because there's no way to solve this algebraically. We're going to have to use a calculator to find this value. It's going to be a decimal value. So let's plug this into y equals pi minus 2x, and then cosine of x, minus 2 sine of x. Now we know that the x value has to be between 0 and pi. So let's go with window. Let's go 0 to pi. And then maybe negative, I don't know, negative 10 to 10. Let's do that and let's see what it looks like. And we'll go by ones. So let's graph this. Now there's the first 0. That's where the derivative is 0 first. And then again over here. Now we're looking to maximize the area. And maximums happen when the first derivative changes from positive to negative. So this is a potential maximum. And right here, the derivative goes from negative to positive. So this would be a local minimum. So we really want that first variable. So we'll go second, calculate a 0. And let's get it over to the left. Then back over to the right. And we'll back up and the x value is 0.710. So x equals 0.710. Now it says, what is the largest area the rectangle can have and what dimensions give that area? So let's give the dimensions. If we plug in, keep in mind that x is holding that value. So if we go pi minus 2x, then the base is 1.721 by, and then we want the sine of x, which is the height. 0.652. 0.652. Now, if we multiply those two together, that should be the area. So we'll take that number times, and we'll go grab this number. And the area is 1.122. So the area is 1.122. Example 3, fabricating a box. And I just made a note that the quadratic does not factor. We're going to have to use the calculator to solve this one. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. So here's the 25 by 20 sheet. And if you cut out x's, length x, on all the corners, you can fold these up and then create the box. A, write the volume V of the box as a function of x. Using appropriate units, what is the relevant domain of V of x? So letter A, the volume in x is equal to, it's length times width times height. So let's just write x times 20 minus 2x times 25 minus 2x. Using appropriate units, what is the relevant domain of V of x? So this is, I don't know, inches cubed, I guess. So let's multiply this out. We have x times 500 and minus 40. I'll write it out. Minus 40x minus 50x, and then plus 4x squared. So that's x times 500 minus 90x plus 4x squared. And then we'll distribute the x through. So 500x minus 90x squared plus 4x to the third. Letter B. Find dv dx. Using appropriate units, interpret the meaning of dv dx in the context of the box. So dv dx is equal to 500 minus 180x plus 12x squared. And the change in volume, which is inches cubed, with respect to x or a side in inches is 500 minus 180x plus 12x squared. Letter C, find the value of x that will maximize v of x and justify your answer. Now we need to set this equal to 0. And I said this doesn't factor, so we're going to have to use the calculator to find the decimal answer for this. We have y equals, let's clear this out, 500 minus 180 plus 12x squared. Now, if we plug 0 in, this is going to be all the way up to 500, and I see I missed the x here on 180x. Insert the x, enter. So the window is certainly going to have to be, I think the x's are going to have to go out to maybe 20. Let's try 20. And then we're going to go, how about negative 10 all the way up to, let's see if 500 will do it. And we'll go by 50s. Graph. Yeah, that seems to do it. Now, we're looking for a maximum value, and when the derivative goes from positive to negative, then we have a maximum value. So we need to find this first 0 here. We're going to calculate a 0. Left bound 10. No, I don't think so. Let's go left with this. There we go. Enter. And we'll go right until those y values are negative. There we go. And we'll back up. So x is equal to 3.681. Find the value of x will maximum and justify your answer. dv dx changes from positive to negative. So letter D, using appropriate units, interpret your answer. Let's see, did I find the value of x will maximize v of x? Using appropriate units, interpret your answer in the context of the box. When x is equal to 3.681, the box inches, or let's see, use appropriate interpret your answer kind of. When x equals, which is a side, which is a length of the cutout, really, of the cutout. When that is inches, the box has maximum volume. There we go. Example 4, designing a can. You have been asked to design a 1-liter oil can shaped like a right circular cylinder. What dimensions will use the least material? Note decimal answers, use calculator. 1 liter is 1,000 centimeters cubed. So we are trying to have the least material, so the least surface area. So the area, or the surface area, is equal to pi r squared. That's the top and the bottom circle. And the shape around it, the lateral surface area, is, it's going to be, if you cut a can on the side and you lay it out, you get a rectangle. Now the top is the circumference, 2 pi r. And then the height is h, we'll call it. So this is plus 2 pi r h. Well, now we have two variables. We have r and we have h. So we want to eliminate one of these. And the volume is equal to pi r squared, the area of the circle, and then times h. And we're told that that's 1,000 centimeters cubed. That's pi r squared h. Now we take h, or we divide by pi r squared. So h equals 1,000 over pi r squared. Now we can replace this h with 1,000 over pi r squared. Now the surface area is pi r squared plus 2 pi r times 1,000 over pi r squared. And let's see, the pi's cancel and one of the r's cancel. So the area now is pi r squared plus 2,000 over r. Well, now we're trying to minimize the surface area. So a prime is equal to 2 pi r, the derivative, minus 2,000 over r squared. And we want to set that equal to 0. So 2 pi r minus 2,000 over r squared. Let's add over 2,000 over r squared. That's equal to 2 pi r. Now we can multiply by r squared. 2,000 is equal to 2 pi r cubed. Divide by 2 pi, so r cubed is equal to 1,000 over pi. And then take the third root. So r is equal to the third root of 1,000 over pi. And it says what dimensions will use the least material. Let's get a value for r. And we'll get out of here. And we want the third root. So math number 4, third root of 1,000 divided by pi. So r is 6.827. That's the radius. And so we need to get the height. Where can we get the height? How about we plug it into here? 1,000 is equal to pi times 6.827 squared times the height. So we need 1,000, and we're going to divide by, actually, we could have plugged it in. Could have just done it right here. Divided by pi times this number, which is r squared. And here is the height. So the height is equal to 6.827. And these are centimeters because we did the volume in centimeters cubed. Centimeters. Maximizing area. What is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and what are its dimensions? So let's draw a right triangle. We'll make the hypotenuse 5, and we'll call this A and B. A and B. So the area is 1/2 base times height, or let's just say A times B. Well, now we have two variables, and we have to eliminate one of the variables, so we're going to have to come up with another equation. But we know that a squared plus b squared is equal to 25. That means we could go b squared is equal to 25 minus a squared. And so b is square root of 25 minus a squared. Now we can make b square root of 25 minus a squared. So now the area is 1/2 times a, and then times the square root of 25 minus a squared. Well, now we have to take the derivative of the area. So first times the derivative of the second. 1/2 25 minus a squared to the negative 1/2 times negative 2a. There's first times derivative of second, and then plus the second times the derivative of the first. A squared. There we go. All right. Well, what do we got? We got these two 2's cancel out, and we have negative a squared on top, and on the bottom is 2 square root of 25 minus a squared. And then over here we have plus the square root of 25 minus a squared over 2. Well, let's get, should we get common denominator? So we need to multiply by square root of 25 minus a squared on the top and the bottom here, 25 minus a squared. So that's equal to, and we're going to set this equal to 0, negative a squared plus 25 minus a squared over 2 times the square root of 25 minus a squared. So 0 is equal to, now we care about where the derivative is 0, so we have 25 minus 2a squared. So 2a squared is equal to 25. A squared is equal to 12.5, so a is equal to the square root of 12.5. What is the largest possible area for a right triangle, and what are its dimensions? All right, so we got a is square root of 12.5. And so that is actually 3.535. So 3.535 by, that is the A, and we need the B. So B, if we plug it in right there, is the square root of 25 minus this thing squared, which is the same thing. So 3.535 by 3.535, and then we just need to go up here and 1/2 times both of those. So let's grab that and square it and divide by 2, and that is the actual area. So the area is 6.25. 6, largest rectangle. A rectangle has its base on the x-axis and its upper two vertices on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have, and what are its dimensions? So a rectangle has its base on the x-axis. All right, so let's put the base on the x-axis. And its upper two vertices on the parabola 12 minus, so this is up here at 12, and then we're going to go down here and down here, which this is negative square root of 12. This is the positive square root of 12. What is the largest area the rectangle can have? So here's the rectangle right here, and that should be perfectly symmetric. So let's pick an arbitrary x value, and that's kind of what we're looking for. We don't know what it is right now. But the base, so the area of the rectangle is 2 times x. That's the base, because if this distance is x, this is symmetric, so that distance is x as well. So the whole distance is 2x. Now, if we knew this, what the x was, the x coordinate would be x, and then the y coordinate would be 12 minus x squared. So this height right here is 12 minus x squared. So times 12 minus x squared. And here we have the base times the height. So let's distribute. We have 24x minus 2x to the third. And we're going to take the derivative. So a prime is equal to 24 minus 6x squared. We're going to set that equal to 0. Add over 6x squared. That's equal to 24. X squared is equal to 4, so x is equal to 2. What is the largest area the rectangle can have, and what are its dimensions? So 2 by, oh, and actually, it's actually going to be 4, right? So 4 by, and if we take 12 minus 4, a 4 by 8, and the area is 32, because it's base times height. Number 20, quickest route. Jane is 2 miles offshore in a boat and wishes to reach a coastal village 6 miles down a straight shoreline from the point nearest the boat. She can row 2 miles per hour and can walk 5 miles per hour. Where should she land her boat to reach the village in the least amount of time? And note, we're going to have to use a calculator. So here is the beach. Here is the boat right there. So the boat's this far. How far off? 2 miles offshore, so 2 miles. And then she can row 2 miles per hour and walk 5. So how far will she have to go here? This will be the distance she's going to row, and then she's going to walk the rest of the distance. Now from here to here, let's call that a distance of x. And if the overall distance is 6, we'll call the rest of this 6 minus this distance right here that she's already traveled. Now this, the hypotenuse is the square root of x squared plus 4. And then that distance is 6 minus x. So the total distance she has to walk, actually, we don't want distance, do we? Where should she land her boat in the least amount of time? Well, rate times time is equal to distance. Now, if we're going to try to minimize the time, that's distance over the rate. So the time is equal to the square root of x squared plus 4 over the rate she can row. So that is, wishes to 2 miles per hour. So 2 miles per hour. And then plus, the rest of the distance is 6 minus x. So 6 minus x, and that's going to be over 5. So we want to take the derivative of time. That's going to be 1/2, so 1/4, right? 1/2 times 1/2. 1/4 of x squared plus 4 to the negative 1/2 times 2x. And then this is just going to be plus x. It's actually going to be, we'll write as plus negative 1/5, but, minus 1/5. And, so we have x over 2/4 is 1/2, 2 square root of x squared plus 4, and then minus 1/5. Let's add over 1/5. So we have 1/5 is equal to x over 2 squared of x squared plus 4, and we can cross multiply. So 5x is equal to 2 times the square root of x squared plus 4. Let's square both sides to get rid of the radical. We have 25x squared is equal to 4 times x squared plus 4. And let's distribute. So 25x squared is equal to 4x squared plus 16 minus 4x squared. So 21x squared is equal to 16. X squared is equal to 16 over 21. So x is equal to 4 over the square root of 21. Now it says, where should she land her boat to reach the village in the least amount of time? Well, we found x. So we need 6 minus 4 over square root of 21. 6 minus 4 divided by square root of 21, and that is 5.127 miles down the shore.